So yeah, thanks for coming, guys. I hope you had a good weekend. It's raining right now in State College, so thumbs down to that one, but it's okay, we'll live. Thanks to everyone who put their Penn State email in the chat box for me. That makes things so much easier. So thank you for that. Let's do some review of Chapter 7 this week. So we've been talking about variables a lot, and now we're kind of talking about what we want to do with those variables. So we're just talking about when we have all of them, we collect all this data, and we want to basically put them on something. We want to show them on a distribution. That's what we're talking about here. And you guys have been doing this with stat key and everything. It's basically the when you guys would like take a bunch of samples and stuff, that was taking all those little variables and displaying it on that normal curve that you got. We've been doing it, but we're just gonna talk a little bit more about it here. Okay, so when we're talking about just normal distributions, this is basically what we've been doing like since the beginning of dinosaurs. So we definitely have been doing this, and you guys probably have a good grasp on it, but it's just kind of another way to notate it. So like when we're talking about normal distributions, this notation here is what we're going to use. It's just talking about our mean and then our standard deviation, just kind of showing it in a different notation here. And then over here on the right, this diagram is showing us our normal z-curve. So remember, our mean is always going to be 0 here. So we would like signify this by n, 0, as it says on the side there, 0, 1, because it's just going to be our mean. And then our standard deviation. And in this case, our mean is 1, or sorry, mean is 0, standard deviation is 1, as it is in every case when we have a z-curve. So that's basically just showing us how we did that. Remember, the total area underneath the entire curve is 100%. If we go back to our empirical rule, we remember how there's different percents of the data that lie within certain amounts of the standard deviation. So like, for example, if we did plus or minus 1 standard deviation here, just as a review, what percent of the data would we have under the curve within plus or minus 1 standard deviation? Pop quiz. Yeah, I can also answer it, but does anyone know? Maybe? Yes. Good job, Jimmy. Good job. Yes. So 60. Yes, and the exclamation point. So proud. Good job. So remember, yeah, this is going to be our 68% according to the empirical rule. So that's where we get that from. So this is just another way to kind of describe the normal distributions. Don't want to beat a dead horse with this one. I hate that saying. I don't know why I just said that, but but basically that's what this whole idea is here. So let's continue. Okay, so ways that we can use the normal distribution. So if we get a normal distribution, we're like, yay, this is awesome, we have it. We can use our empirical rule, we can use all that fun stuff in it. Basically, these are just different ways we can use it in terms of having that normal distribution. So first thing, if we look at here, we can do confidence intervals. So remember, we've been talking about these for a while, but just as a review, we always have our point estimate plus or minus z star times our standard error. So, and in this case, so I would usually write 2 for z star, because at the beginning, that's kind of what we would always talk about is for our confidence intervals, it'd be a 95%, and so it would be a standard error, or a multiplier of 2. But in this case, I'm starting to write z star because we are starting to use different z stars in this case. So if we have, you know, a 90% confidence interval, we use like 1.645, that kind of thing. So that's why, you know, we're starting to just want to make sure we look at this multiplier as whatever it can be, dependent on what your whatever your confidence interval is. So let me see. So yeah, so our point estimate, remember, is going to be p hat or x bar, and that's always going to be your center. So when we're looking at our normal distribution and we're trying to make this confidence interval, wow, that's a good one. Take a screenshot of that one, guys. This is good. So when we're trying to find this, our middle part right here is either going to be p hat. Well, I don't like that. I want it to be clearer. This middle part here. So this is either going to be p hat or we're going to have x bar. Okay? And that's our middle of the data, our mean. So that's what we're using then to find our confidence interval. We're taking our multiplier times our standard error. So that's going to give us values that end up here and here. And that's how we get our lower and upper bounds there. So that's the main idea there. We're basically taking our point estimate here and finding how far below and how far above it creates that confidence interval of whatever percent we have. And like I said, for our multiplier, since we're not always going to use 2, unfortunately, we are able to find it with our test statistic equation. So that's just a way that it's just another way that we can find our multiplier if we're not using stack here or anything. It's just a way you can find it by hand. Just keeping in mind that it is going to use, your null parameter, and then so what you got from your population, and then the statistic that you got from your sample, and then divide it by your standard error, which is basically saying like how much error on the left and right you have. So that's where we get that. And then lastly, our standard error is what we basically calculate that using our rule of sample proportions or the central limit theorem. So, these are basically what rule of sample proportions are self-explanatory. It's literally just saying that we find our standard error using the rule that when we take a bunch of samples from a proportion, like as long as we take enough samples from it, then we're able to assume that's on the normal curve. And same with central limit theorem, which we'll talk about, as long as it has as long as you have a large enough sample size, then we are able to also assume normal distribution. Math did not work there. Okay, so so now just to talk a little bit more about central limit theorem. So this is when we're talking about means. This is talking about when can our sampling distribution for mu, so remember that's going to be our population mean, be estimated using a normal distribution. So remember what I said, when you take a bunch of samples and then display them on a graph, that's going to be our distribution. So we're saying basically, like when you're taking a bunch of samples, displaying them, that's going to be your sampling distribution. You're wondering, okay, when can we use that? And then when can we assume that it's going to be used with a normal distribution? Like how big does the sample have to be? Does it have to be small? What are the different conditions? So that's basically what it's asking. So central limit theorem in general is just saying that if we have a large enough sample size, then our distribution of sample means is going to be about normally distributed. And also keep in mind, this is regardless of the shape of the population. So don't get tripped up if you see a skewed population, maybe it's left skewed, and you see your data is all spread out on the left side there. If you do have a large enough sample size, what the central limit theorem is saying, that even though it's skewed, we can just take a bunch of samples with that large enough sample size, and we will be able to assume it to be normally distributed. It's basically saying that a large enough sample size will cancel out any type of skewed data that you have. So that's the main idea there. That's one thing to keep in mind. So, okay. All right, so binomial random variables. So these are just another type of special variable because there's so many of them. But so they are discrete random variables. So remember, discrete goes along with quantitative variables, and that means it has to take on a set number of values. So we are talking about they can't be, anywhere on a list, basically. There are a set number of values that these variables can take on. And the main thing of what they're doing is they're just counting how often something occurs. And the definition kind of encompasses the 3 types of conditions that have to be met. But I'll say them anyway. So our first one is that we have a fixed number of trials, so our fixed sample size. And then our probability of a success has to be the same on each trial. Meaning that when you take, and then this kind of goes along with the second or the last one. So if the probability of success is the same on each trial, that means that if you do a trial and the probability of gaining success is 0.2, on the next one it also has to be 0.2. And this will happen if they are independent of one another. If you think about it, because if they were dependent on one another, then those probabilities may change dependent on what if they are interacting with each other. But if they don't interact, then when you take one sample, that should have nothing to do with the next one you take. So the probability of successes should be the same on each trial, then it won't be influenced by each other. So those two kind of go hand in hand, but those are just basically the 3 main conditions that we have in order for something to be considered a binomial random variable. Okay, so this is a beautiful equation called something we're not going to do, but you'll have to, it's better to, I always talk about this, so you guys want to make sure you understand the concepts of these kind of things, so that when you're plugging in things into Minitab or stat key or just an equation in general, you kind of understand the background behind it, because then it makes the questions make more sense. And then if you get a wrong answer, you'll kind of know right away because you'll realize it doesn't make sense. So, but yeah, so basically all this is saying is that how we would compute the probability that x is exactly a certain value by hand. So, so yeah, this probability of x equals, and then k is going to be whatever the value you're looking for, so the number of successes. So remember that this this has to be fixed. Our number of trials and then our number of successes obviously have to be fixed, and this makes sense too, and this is why you want to keep in mind, remember in our conditions we do have to have a set number of trials and the probability of success has to be the same on each one. And this makes sense because in order for us to do this equation, like these numbers have to stay static for us to like find this equation. You know, we can't be switching these numbers up or else this wouldn't make sense. So basically you need these to be the same exact thing on every single trial. I mean, the main thing I always look for first is to see if they're independent of one another. I mean, remember when we like tested for independence with those 3 different equations where it's like probability of A times probability of B equals probability of A and B, and if it's true, then it's that means that it's independent, whatever. But you can also look at something too if it, you know, if you see something that says like the weather forecast in Jamaica and then the weather forecast in Alaska, like are they independent of one another? Theoretically, you can say yeah, because what happens, as long as we're not talking all sciencey and stuff, you know, whatever happens down there isn't going to be affecting what happens up, you know, in Alaska. So it's one of those things I always try to check for independence first, because then if you start to think about that they might not be independent of one another, then you can kind of go through and start deciding, okay, maybe the probability of success isn't the same on each one, maybe it's different because they are dependent. And then fixed number of trials is a very obvious one. Like if you don't have a fixed number of trials, you don't have a fixed number of trials. So yeah. Oh no. Okay. I think I just accidentally hit airplane mode on my thing. I hope am I still here? Is everything okay? Ooh, that was really scary. Okay. Let's clear this. Okay. All right. So can everyone still see my screen? Is it still shared? Everything's okay. Okay. Whew. Thank the Lord. Okay. I was like adjusting the thing. Oh no. Oh no, what do you mean? Oh my God. That's not funny. That is not funny. I was so concerned. I was like, no, I have already started recording it and now everyone, you guys really, you're gonna get me. Oh, my goodness gracious. Well, that was your question last week, Jimmy, too. Hello. So, you know, I'm glad you had a new question this week. Seriously. Oh, I swear, I know. Yeah, you guys are going to give me a heart attack. I need a Gatorade or something. Okay. All right, let me know what I'm talking about now. Okay, so let's talk about when we're doing our mean and standard deviation. So basically, these are plug and chug equations, very similar to what we've been doing. But like I said, try to understand them conceptually. So for our mean, you know, it's our n times p, which is our sample size times our probability. So that makes sense because it's basically saying like the probability of getting that sample size, which is your mean. That's going to be like your most frequently occurring value there too, in the middle usually, if it's normally distributed. So yeah, and we also call that e to the x. So that's our expected value. It's basically what we expect to get, because it, once again, if you think about it, you're taking the your sample size, how many like items you have, how many samples, and then times the probability of a success. So if you multiply those, you're going to get a value which is technically telling you your mean, because it's saying the probability that you'll get that like number of successes, like the number that you'll get in all those successes, or the fact that you'll get that success in like all those numbers. And then so it's like your expected value. It's what you're expected to get given what your probability is on each trial, and then also how many trials you have. And then on the right, we have standard deviation of a binomial random variable. And so yeah, we just have sigma and then times, or square root of np times 1 minus p. You'll see that equation very often. You'll see it used for the stuff under the square root. You'll see that often used for, I don't believe we just talked about this yet, but if we're talking about like successes and failures and like proportions, the rule of sample proportions goes into a little bit more. I'm pretty sure that's next week, but yeah, so you'll see that often. So that's something to definitely kind of get a hold of and understand. So But remember, our mean is our center, and then standard deviation is our spread. So, oops. Oh, I just saved my screen. I'm a hot mess tonight. It says screen has been saved. Good. That's great. Okay. Oh my goodness. Are we sure we're at review question? Let me just make sure, because now I feel like I did some. All right. Yeah. I guess we're at review questions. Okay. Let's do these things. So if you've already done them, do them again. So I'm not by myself. I'm just kidding. Do them if you want. But all right. So let's look at this one. So this is binomial random variables. This is like basically a table representing the probability of these things. So go ahead and try to compute the probability that x is less than 3, and we will go over this one then. Yes, good work, everyone, as per usual. You guys are geniuses. Okay, so let's just look at this one. Actually, I'm going to ask some follow-up questions because you guys are smart, and I think it'll be fun. So let's do this one first. So we have a probability of x is less than 3. Okay, so what if we look at this here, and we want to figure out what part of this table is less than 3. So we have 0.41 that is equal to 3, so we don't want that. We want everything to the left of it, okay? So all we want to do is add these up, and then if you add them all together, you get 0.59. Happiness. So yeah, so that's how we do that, because all we're talking about is the values that are less than 3, which includes 2, 1, and 0, but does not include 3 because we're just talking about less than, but not equal to. So good job. Amazing. Oh, wait, I think I have another one. I think I knew you guys would do good, so I have it. Yes. Oh, yes. Okay, try this one. Probability that x equals 3. Let me know what you think about this one. Yes. Good job. Okay, so absolutely. So our answer here is 0.41 because all we're talking about, and if you look at the top of the, can this work? Okay, yes. So here we say, it, over here, it literally says probability that x equals x. So technically, it wasn't a trick question. It's a very, you think it's a trick question because you thought too hard about it. But really, it's not that hard. Yeah, I know. I just told someone this morning in the Q&A, I think they were trying to find a confidence interval or something, and they were in Minitab pressing all these things. I was like, so just use the equation, the confidence interval equation. Like, oh yeah, I guess we could do that. So always think simplistically first in statistics, because in the end everything does come down to the simplest stuff. Actually, I was reading today an article, because that's what I do in my spare time, and we talked a lot about, and I'm going to actually discuss it with you guys when we get to chi-squared, because I want to show you statistics in real life. It's a thing. It exists. So like, I was literally reading an article and it talks about like statistical significance and p-values, and it's like, yes, that is us, guys. So it happens in real life. So be happy you're taking this class, because you'll see it and be like, yes, that alpha level is lit. So if we were looking at this, if we were to look at each like value that I have on this top row here, technically this is saying, like for this last one, the probability that x equals 3, because it says probability of x equals x. So the probability that x equals 3 is just 0.41. So that's why that's our answer. So then what would be the probability that x equals 1 in this case? Pop quiz. Anyone want to answer it? I can answer it too if you don't know. Just tell me you don't know, or else I'll just stare at you guys. Yes, thank you so much. Yes, absolutely. So our answer is 0.24. Probability that x equals 1 is 0.24. Raise the roof. Okay, let's do, I'm sorry, you guys are smart. I'm just going to throw this at you just because I think it's important. Okay, what's the probability that x is greater than or equal to 0? Try this one. Well, let me know what you're thinking. Yeah. Okay, yay. So let's look at this. So remember, all of these values, so this is the same thing. We're talking about probability still. So let me erase this because it's too much going on. So we're still talking about probabilities. So when you add up all the probabilities of something, what do they have to equal? Yes, absolutely. Yeah. So when you add up all the probabilities, we do have to have it equal to 1. So in this case, we ask the probability of something is greater than or equal to 0. So that means what? We're going to include 0. I'm like, okay, so we want everything that's greater than or equal to 0. So that includes this, and this, and this, because all these numbers are greater than or equal to 0, including 0. So all you do is add all of these up. And I mean, you can add them up, but you have to know, too, that all of them together have to end up equaling 1 in the end. So our answer would be 1, because the probability of getting anything greater than or equal to 0 in this case is 100%. You're always going to get something greater than or equal to 0, if that makes sense. Because that's what I'm saying, like, think about it logically. So we're trying to figure out, wait, I don't want that to confuse you. So yeah, we just did probability that x is greater than or equal to 0, which is equal to 1. So, because if you think about it, it's literally saying, what's the probability that we pick something, or that, like, the number that we get there is 0 or anything higher than that? And if you look at it, that's everything on the graph, because 1 is higher than 0, same with 2, same with 3, and 0 is equal to 0, obviously, so we include it. So that's why we add them all up to get 1. Does that make sense to everybody? Nice. Superb. I need some new vocab. I say like cool a lot, and that's just, it's not good. All right. Let's see. Okay. Let's do another one. Woo. Okay. So according to a 2001 study of students by Harvard University School of Public Health, 19.3% of those included in the study abstained from drinking. Suppose that all current college students in the United States, 20% abstain from drinking. A random sample of 4 college students is selected with the following binomial results. Also not a very good sample size, but doesn't really matter right now. Okay, so from this table, similar to the last question, just set up a little bit differently. What is the probability that exactly 2 college students in this sample abstain from drinking? So go ahead and let me know what you think about this one. I'll write a few other questions while you guys are looking at that one. Yes, raise the roof. I guess I also say that a lot too. Yeah, I need some new vocab. I'm gonna buy myself a dictionary or something, or a thesaurus. Sounds like a type of dinosaur. But yes, great job, guys. Absolutely. I think we lost Jimmy. Very sad. Jimmy, please come back. We miss you. But so yeah, the answer here is just going to be whatever this value is. So it kind of shows you that it's like split up into 2 columns here. So our X, remember, is our number of successes. So, oh my, Jimmy raised his hand. How did, same, but how'd you do? I'm going to do that. How do you do that? Let me see if I can do it. Click on my little thing. Rename, hide myself. What? Guys, 2 participants raised their hands. I'm nervous. Okay, well, thanks for letting us know you're alive out there, Jimmy. I was concerned. We missed your intelligent answers. But yes, I'm sure you understand why this is 2. It's literally just showing you, because remember, X is going to be your number of successes in terms of this probability of X equals X situation. So it's just showing you that. So right here, we're basically showing the probability that X equals 2. Because our X here is 2. Oops, and then that's a probability. So that's our answer. Yes, good job, people. So proud. Okay, and then can you rewrite it down here? I just, for a follow-up question, because I'm feeling, oh my goodness. Do I pronounce your name Lan? I don't want to pronounce it Lan. I don't want to pronounce it incorrectly. I'm a speech pathology major. That's important to me. I just like Marie and Jimmy are just like, yeah, those are my names. Yeah, yell at me if I pronounce it wrong, please. But yeah, that question down there, we have a probability that at least oh, okay, perfect. Okay. Well, great job. Super smart. So yeah, the probability that at least 3 college students abstain. So what would our answer to this one be? Okay, yes, I see your thought process. I'm like still not good with this. Ooh, look at me erase so quickly. All right, that was fun. Okay, so when we're asking this question, draw, please. Okay, so probability that at least 3 college students abstain. So that's talking about, so when you say at least, we're saying that amount minimum, basically, or more. Okay, so that's going to be probability. So we're saying at least 3. So that X is, so we want to be, it can be like equal to 3, but it can also be greater than, because it's at least. Okay, so at least 3. So what we want to do there is actually, And Lane, I totally see what you did there. Yeah, like that's actually a really smart way to do it, because you're recognizing that our entire probabilities, like these all together, have to equal 1. So if we're looking for, you know, these values down here, definitely do what you did there, 1 minus 0.0016. That's going to give us the probability that 3 or less are drinking. That's what that probability is. Or the probability that I guess you could say that no more than 3 people drink, so it could be that. But in this case, since we're talking about at least, that means that at the minimum 3 college students, but it can be more. It's just saying the minimum is 3. So what we're looking for here, in that case, we're actually just looking for these numbers up here, because we're looking for at least 3 or higher, which could be that one. So all we would do here is add up 0.0256 plus 0.0016, and we end up getting 0.0272. Yes. Does that make sense? I also just made this up right now, so if I did it wrong, let me know. But I think it's okay. Yes. Okay, cool. I almost said raise the roof again. I need to stop. All right, let's check out raise the roof. Yes. That's what I do when I'm done with exams too. I'm like, Okay, that's enough. Sometimes I forget, like I post these on YouTube too, so everyone gets to relive these moments that I try to forget about myself, but that's okay. We will. It is okay, everyone. We're all in this together. I know, you're right. I need to get famous on YouTube. That's all I have going for me at this point. I show grad schools, I'll be like, I'm famous on YouTube. Let me in, please. For something that's not even my major, but that's okay. It's still a good time. All right, let's do a few more of these. All right, so for a given binomial random variable, n equals 12 and p equals 0.6. So please compute the mean and standard deviation of this. And think about it conceptually while you're doing it. But yeah, let me know what you get for these answers. Yes. So beautiful. Wow. Okay, yes, let's go over this. Good job, guys. Definitely got this under wraps. So our mu, our mean, remember, is equal to our n times p, our sample size, times our probability. And then we have our sigma, our standard deviation, which is our square root of np times 1 minus p. And think about it. I'm getting a little ahead of myself, but I think you guys deserve a preview. Just think of statistics like a movie, and I'm just giving you a little spoiler here. So you have your probability. So your probability is your probability of successes, right? So can anybody just kind of think in their head, maybe, I don't know where else you would think, but try to maybe think, what would 1 minus p be representing? If our probability is our probability of successes, what would 1 minus p be? It's okay if you don't know. I just thought I'd mention it because we'll talk about it later, and it's kind of relevant right now. Yes. Yes, Jim. I knew. See, that's why I asked, because you guys, A+. Yes, that's right. Exclamation points. Good job. Absolutely. So yeah, that's going to be our number of failures, because just like Lon showed us earlier when we did that, like 1 minus whatever number we don't want, that's going to show us our number of failures, basically everything else. And probabilities, we did it with complements. Yes, raise the roof. Good job. So yeah, 1 minus p is going to be our failures there. So that's to keep in mind kind of what, like, conceptually where our sigma is coming from. So see, our n times p is that's our successes, but then times 1 minus p is also our failures. So it's kind of showing you the spread of the entire graph thing going on, the entire distribution, because you're looking at all of them. So, but yes, good job. Wow, I'm crying. Okay, so then just to do this, we just have 12 times 0.6, which you guys are correct. We get 7.2. And then if we were to do our sigma for our standard deviation, we would get 12 times 0.6 and then times 1 minus 0.6. Boom. Okay. Yeah. Oh wait, I never put the answer. Okay, yeah. 1.697. Awesome. Oh my gosh, I almost dropped something. Okay, yay! Good job, guys. Absolutely. So let's do another one. Oops. My bad. Okay. Yay. Okay. SAT math scores have a mean of 500 and a standard deviation of 100. Apply the empirical rule to find the range of the middle 95% of SAT math scores. You know I love my empirical rule, so let's apply it. Let me know what you guys get for this one. Wow. Wow. Amazing. Beautiful. Flawless. Okay, yes, good job. So, wow, and Maria's just going ahead and giving us that interpretation. It's just, okay, so let's do a throwback Sunday to our empirical rule really fast. So here we got, boop. All right, so if we have our mean of 0, as per usual, and then we're talking about our 95% confidence interval, you guys obviously know that it's within plus or minus 2 standard deviations. So, color on it. So this is going to be 95% of our data, okay? So, if we were to standardize this, and we were to take, oh, that's not good. Let's do it again. Okay, if we were to take the math scores that we had, it looks like a spaceship. Okay, we're going to start here, and we have our mean of 500. And then our standard deviation is 100. So what we want to do, though, is we want to go out 2 standard deviations on either side in order for us to keep in mind this empirical rule up here. Okay? So then all we have to do is minus 200, because it'll be 100 plus 100. So we're going to get 300. And then add 200, so we get 700. So, as Maria said, we are 95% confident that the population, that the population mean of SAT math scores is, oh goodness, between 300 and 700. So that's our interpretation in the end. So remember, good job, Maria, remembering that we use population. And we're talking about means here, not proportions. These are whole numbers, and they're not decimals, like between 0 and 1. And we're not talking about like a percent of anything. They're like actual numbers. So yeah, that is our range. Wow, amazing. Super proud. You guys did a great job. Okay, so that's all we have. Sad, but obviously check out the YouTube. It's the only thing keeping me going at this point. But we had that, and then our next review will be on Thursday at 10, I believe. Yes. Oh, I have a grad school visit that day. I'll be back, don't worry. Yes, we will do that on Thursday at 10. And yeah, if you have any questions, let me know. We can go over those now. If not, Thursday's the day. Or obviously Zach has his Q&A hours. I'm not sure what they are because I don't attend myself, but they're on the website. I think everyone gave me your Penn State email, so thank you for that. Thanks for coming and keeping me company. What else? Yeah. Thank you so much. Yes, have a great night. Have a great night, all y'all. And a good Monday. I know Mondays aren't the best, but yes, enjoy your week.